Okay, I'm going to start recording for chapter 7 on this of the understanding photovoltaics. So let me jump straight in there. I'll probably, what I'm going to do here, because we're going to spend a fair amount of next week talking through some of the math problems. So I won't be really looking at the mathematic problems today. I'll just get a head start on it. But in the meantime, usually it's the math where we're walking through doing system design that people have the most problems. So next week, I'll try and walk through and actually do a few of those designs and math problems. Okay, the voltage drop of a system is too great. What can a system designer typically do to fix this problem? And we've mentioned this before. Usually with voltage drop, the issue is the wire is either too small or the distance is too great. So basically, you could increase the size of the wires out of these. The rest of these are not going to have any effect on it. So as a designer, usually your best option is to just increase the size of the wire. And the only reason why you wouldn't go with the biggest wire available is just cost, system cost. Which of the following is considered the maximum current a panel can produce under standard test conditions? And that's going to be the ISC, the amps short circuit. That's the maximum current. And the reason we use this number, it's a theoretical number because, well, let me go ahead and draw a picture here. You remember with the IV curve basically says, here's your IV curve. This is amps, this is volts. And essentially the curve is going to look something like this. And the maximum amperage is going to be the ISC up here. And the maximum theoretical voltage is going to be the VOC down here. Well, since this is a curve with this being 0, any number times 0 means you're going to have 0 watts at the ISC. And the same thing, 0 watts at the VOC, because any number times 0 is 0. So neither of those conditions is a good condition, obviously. So the system will be broken. But we use the ISC as the maximum. So when we're doing our design work for wire size and the like, we'll use the ISC because that's the theoretical maximum worst case condition. Somewhere in here would be the Mppt, maximum power point, sometimes referred to as the Pmax. And then there is a voltage associated with that, which is the Vmax or the VMP, the voltage at the maximum power point. And then there's an amperage, which is the Imax or the IMP. They haven't really standardized on these acronyms for those two, but that's the amperage at the maximum power point. John, you had a question? You're muted. If you're going to have to unmute. I see you waving there. Yeah.
Here we go.
There's timing.
Hang on. Hello. Yes. Yeah, is this in person or remote?
Okay, I'm going to mute him and keep going on. All right, so basically this is your IV curve, and you've got the numbers that we're worried about, the ISC, the theoretical maximum amperage, the theoretical maximum voltage. We use the VOC because when we're designing our systems, remember that in a residential, the maximum voltage is 600 volts. So we'll use the VOC for that. John, you ready for your question? Don't see you there. All right. So when we're designing for voltage, we're going to use the VOC because that's the theoretical worst case scenario. For amperage, for the wire size, we're going to do this. but the operating is going to be the Vmax and the Imax. Yeah, John, you had a question?
Okay, so if you put a clamp on amp meter while you shorted the panel out, would it be reading the maximum amps? I mean, I'm kind of having an issue with this because you have maximum current with no voltage. So is there current flowing or not?
I
See what I'm
don't
saying?
think, I think the ISC has to be a theoretical number.
Okay.
The
So when you
VOC,
short a panel out, it's not producing power.
yeah, but
It's
in
not
order
gonna
to,
burn itself
in
up.
order, in order to measure amps, you have to have current flowing, right?
Well, yes. And
So
with no pressure, no
I think,
volts, no flow.
I think you could measure somewhere close to ISC, but never actually at ISC because you'd have 0 amps or 0
So
watts.
the other question is, if you short a panel out, it's not going to burn itself up.
When you say short a panel out, do you mean connect the positive lead to the negative lead?
Yeah, well, I mean, it is ISC, short circuit. That's what it is, current
Yeah.
short circuit.
Yeah, you may know more on this. I do know you can hook up the positive to the negative lead together.
Okay, we'll try it over at Tim's house. We'll find out.
Yeah, it will not, no power will flow unless there is a load to service. So
Okay,
if you
well,
shorted it, it would have to short to ground.
it's counterintuitive. So this is something I got to ask. All right, good enough. That's all.
Yeah. Now you can measure the VOC. If you were to take a solar panel and put a voltmeter on the positive and negative leads with no load attached, you will get the voltage open circuit or the open circuit
Right.
voltage.
That's what I understand, open circuit.
Yeah. But the ISC, I have a feeling it's a bit like absolute zero. It's a theoretical number, but you can never actually get there.
Yep.
Okay, so let me go back to the here. Okay, so we just use the ISC for the design purposes. To account for the inefficiencies of a PV system as the result of voltage drop, loss due to connections, inverter inefficiencies, internal battery load resistance, and other items, you must what? Well, you need to derate the estimated power output. And it really is going to vary a lot as to what the derate factor will be. When we get into this for our design work, a lot of folks always ask, well, what should I derate my system? And that becomes something you just get used to doing based on the materials you're using. But what I typically will do is estimate about a 2% voltage drop. And then you look at what your inverter inefficiency is, and you'll get that number from the spec sheet on your inverter. In the old days, a 90% efficient inverter would be quite good. But today, these inverters are closer to 98, 97, 98% efficient. So you'll often find that you'll really only have maybe 3% on the inverter, 2% on your voltage drop, throw in another 1 or 2% for connections, switches, things of that nature. So you're going to find that you're derating somewhere in the neighborhood of 7-8%. If you really want to be conservative, you could derate 10% for a grid-tied system. If there are batteries in there, the batteries will add as much as 15% derate for lead acid batteries. So you'll have to factor that in. And charge controllers add another 1% or so. So you'll just have to kind of, it's like an inefficiency budget. You'll put that together and find out what you have to derate your system for. When an unintended pathway is created between the PV array and a grounded surface, this is known as a ground fault. Okay, that is a bad situation, obviously. With PV, one of the leading causes of ground faults, you will find wires getting pinched out there because of wind or just the motion of the world. That happens occasionally, and you may find that the insulation is worn through and it's shorting out to the metal of your system. More often than not, though, it turns out to be a rodent, like a squirrel, that's come out and started chewing on the wires. It's my understanding they're attracted to the electromagnetic force, the EMI, of these systems. So if you find a squirrel hanging by its teeth from the wires, you probably found your ground fault. Now, most inverters will have ground fault detection devices. So if there is a fault, which basically means power is going to be running through your grounding system, which is not intended to, but it's going to earth, it's a safety thing to redirect that power to the ground. Your system is designed to automatically shut down. So your inverter will shut down, and there should be some sort of indication, either a light or an email or something that will tell you, hey, there's a ground fault and you need to fix it. Yeah, John. You'll have to unmute again.
Do you know how many milliamps that's calibrated at?
How many milliamps? No.
Like a GFI in a house is 6. A gutter class B is 25. I just wondered if they know.
It would probably be in, it would be in your inverter specs, I would imagine. Because your GFI, your ground fault interruption is always going to be included in your inverter.
Okay, well, we'll find that out someday. All right, thank you.
Okay, thanks. When sizing a battery bank, its storage capacity is measured in, and of course it's measured in amp hours. Remember that panels only generate power, so they're measured in amps and volts. The batteries store energy, so they're measured in volts and amp hours. Amp hours is just the way you would measure the stored capacity of a battery. And often with lithium ion batteries, what they're starting to do is they measure those in kilowatt hours. They just simply multiply out the volts times the amp hours. Which of the following is not a circuit in a typical grid-tied PV system? And of course, the answer here is PV input circuit. I always like to joke that the input circuit is the sun. It would make a little bit of sense, but if you look at a typical grid-tied system, you're going to find that the area between the panel and the combiner box or the junction box is referred to as the PV source circuit. Then the circuit that goes from the junction box to the DC disconnect, which oftentimes is integrated in with your inverter, but it's supposed to be within 10 feet of your inverter. That's the PV output circuit. Then from the DC disconnect to the inverter is the inverter input circuit. And as I mentioned, if you've got an inverter where these two are integrated, of course, that's going to be built into the unit. So you don't even do anything with the inverter input circuit. It's just built in the unit. And then the inverter output circuit is essentially all of the AC wiring from the inverter to the service panel. And the inverter will connect into an AC disconnect. And as we'll mention, the AC disconnect has to be located within 10 feet of the electrical meter, has to be externally operated, and it has to be well marked. So the purpose for those requirements is if a first responder comes to the house, or let's say your utility company comes to the house and wants to shut off the service, often the very first thing they're going to do is pull the electric meter. So they're going to come to the electric meter and they're going to see a label on the electric meter that says, warning, this home or this building has a secondary power source. Often the label will say a PV system, but it will say it has a secondary power source, which basically tells them pulling the meter may not be enough. So then they look around, well, it's got to be within visual sight within 10 feet. They'll see this AC disconnect, and this will say, main photovoltaic disconnect, and it needs to be externally operable so they can just pull the arm down, turn it off. So, so that's where the location. Yeah, John? I got you muted again. You're still on mute, John, if you had a question.
So in a micro inverter setup, you wouldn't have the disconnect and the inverter, right?
You mean
If
the
you have
DC
micro inverters on your panels,
Yeah,
you wouldn't have that first disconnect and the inverter. So
right.
you'd only have the solar inverter disconnect, whatever you want to call it.
Yeah, what you would end up having is at your panels, in theory, the PV source circuit would be the wiring from the panel to the inverter, which is just the pigtails from the panel. And then
Right.
all the rest of it would just be inverter output circuit. So it would come from those microinverters to a combiner box or a junction box, and then it would go straight to the AC disconnect. And then it would go from the AC disconnect to the service panel, typically.
Right. Okay. And so then the question, I guess I'm also thinking through why. The reason why we're putting the inverter disconnect on the load side of the inverter is because that could be a battery system that even without the panels, you'd be generating electricity. So you want to kill it from the load side of the inverter regardless.
Right. I think it is a bit of a legacy thing because in the olden days, before the inverters had the anti-islanding provision, the code said you've got to turn them off. And I think the code is slow to adapt because I think what you're getting at is as soon as I would pull the meter, it would lose sight of the grid and the anti-islanding would shut it down. And that's true. So I think that the AC disconnect is just a legacy issue, but it still is the code.
Okay.
All right. Okay, maximum DC voltage for a residential grid tied system in the US that can be configured by code is 600 volts. And this again, I believe is a legacy thing. I think that when the code officials started writing about PV, they didn't really understand photovoltaics, and not understanding it, they decided to link it as part of their low voltage, which is, from my understanding, 600 volts or less. In Europe, most systems are going to be 1,000 volts, and commercial ground mounted systems can be as much as 1,500 volts. There's nothing inherently less safe by having a 1,000 volt system versus a 600 volt system versus a 1,500 volt system. You just have to assume they're all going to kill you if you do something dumb. So it really, but by going with the higher voltage, you have lower amperage for the same size system, and you would save some money on your design and installation if we could go with the higher voltages. But the law at this point still says that it's got to be 600 volts for residential. We keep thinking that's going to change in the next edition of the code, but each 3-year cycle, it stays in there. So we'll just have to wait and see. The maximum DC voltage, an accessible battery bank with a residential standalone system can be configured is 50 volts. And the key term here is accessible. So if you're designing just a regular old standalone system, then you've got a 50 volt DC max. But in the 2020 code, they did say that you could go, if you had an energy storage system, and that's a different term that they use in the code. And I read through this a lot and couldn't really find what the distinction is between what they would consider a battery bank and an energy storage system, other than it's like a commercially manufactured unit. They said you can go to 100 volts. But if the terminals of this ESS or energy storage system are inaccessible, meaning they can only be accessed by a certified technician from that manufacturer, then the voltage is unlimited. And I think that was through lobbying efforts on the part of some of the battery manufacturers like Tesla, for their power wall, or LG Chem for their battery bank. And so they wanted to try and push the voltage up to 600 volts or even 1,000 volts, just to be compatible with the arrays that they were hooking into, because then they didn't have to step up or step down the voltage. So it made their job a little bit easier. All right, Emt Conduit stands for electrical metallic tubing, just something to remember. We use EMT quite a lot in solar. In fact, all DC wire within a building must be contained within metal conduit, which is a strange requirement to my way of thinking. And John, as an electrician, you might know better why. I've asked people over and over and never really got a satisfactory answer. Why can I install AC power inside a building in PVC conduit, but the code requires that DC cable or DC wire be installed in metal conduit? I don't quite understand that requirement, but there you have it. So, yeah.
Well, I doubt that it's a requirement based on the physics of electricity. I suspect it is far more a way for a homeowner to understand that all that metal pipe is not stuff he wants to mess with. I'm just guessing that's what it is, just to make a distinction between his Romex house wiring and all the solar stuff is all in conduit. That would be my guess.
Yeah, I don't know. I mean, yeah. But we did get the authorization in, I think it was in the 2017 code, that you can use MC cable or metal clad cable for DC
Right,
wiring.
well, it's the same difference. I mean, very few houses are wired with MC. So, I mean, it's probably the same difference, just to make a distinction for whoever that is not an electrician to know the difference. That would be my guess.
Well, it's a big deal. The MC stuff was a big deal for solar installers because it meant they didn't have to then do all of the EMT conduit bending and fittings and everything to run a wire through the attic and down. So most installers today use MC cable for their inside DC wiring, just because it's a lot easier to work with, a lot easier to make all the bends and turns and all of that kind of thing. And if you're not familiar with MC wire, it's basically, it comes pre-configured, and it's got the sort of the loops of metal clad around the wires themselves. Looks a little like I don't know, like a Tootsie Roll, I guess. Yeah, John.
Well, the other thing too is I doubt that they're worried about some kind of magnetic field, because when they said MC cable was allowed, they didn't specifically say it had to be steel. You can get MC in either steel casing or aluminum casing. The aluminum casing doesn't suck up the magnetic flux, whereas the steel would. So if they didn't make a distinction in that, then it probably got nothing to do with concern about magnetic flux escaping. So I'm guessing it's got to be just to make it look different and make it easier for those non-electrician people to differentiate between what is DC and what probably isn't. That would be my guess.
Okay, and also when we get into the labeling portion, it is also required that every 10 feet on your metal conduit, it must be labeled as photovoltaic circuit, and within 1 foot of every bend and wall penetration. So they seem very, very keen on you making sure everybody knows that's a PV circuit. So you might be right, but I still don't see the logic to it myself. But, you know, who am I to question? They never asked my opinion, so I guess I won't give it. Okay, to determine the maximum panels allowable in a string of grid-tied array, you must know all the following except. So when we go to do the array, the grid-tied array, we need to know the coldest temperature ever experienced on the site. We need to know the voltage of the inverter, the temperature coefficient of the panels, but we don't need to know the azimuth. We don't need to know that orientation. And so when you're figuring out maximum number of panels in a string, that's one of the math problems that we'll get to. Hopefully you've had a chance, all of you, to go through that. If not, the reference pages are right there. We'll touch on that in a little bit. All grid-tied inverters must be rated for at no more than 48 volts, be UL 1741 listed, incorporate modified sine wave, or be rated at 125% of the output. Well, the answer here is UL listed 1741. Obviously, grid-tied inverters have to match the voltage and the sine waves and everything on the grid. So 48 volts, that's clearly not going to be the case for the grid. Also, modified sine wave is not what you're seeing on the grid. So those would be references to standalone systems. The 125%, that's a wire thing. So really what we do require is everything be UL 1741 listed, and that includes provisions like the anti-islanding provision, the ground fault protection provision, that's part of the standard. So every inverter's got to have ground fault protection. It's got to have arc fault protection built into it. So if your system is I guess, looking like it's going to arc, the inverter will clamp it down. So there's a lot of stuff within that standard that has to be, so everything within the system has to be 1741. If you have a wire length of 100 feet in a 90 volt, 8.5 amp derated circuit, what is the smallest wire size you need to get less than a 2% voltage drop? And this particular thing, you know, we've got some of these questions, in case you haven't noticed, you can click on and you can find that there's a hint. So this hint is basically telling you this is going to be using the voltage drop equation. So if your voltage drop equals the amps times resistance times twice the distance divided by 1,000 feet, and we're being told the amps are 8.5, the resistance of the wire, well, in this case, we've got the resistance is built into the answers. It says like a number 6 gauge with resistance of 0.51, so on. So what you could do is you could say, start right at the first one, plug in 8.5 times 0.51 times 100 times 2, so 200 divided by 1,000, or 0.2. And then you're going to find that you get a number. You divide that by 90 volts to find out if it's less than or greater than 2%. You're going to find that it's less than 2%. Well, that meets the criteria, but the question is, what's the smallest wire? And 8 gauge is smaller than 6 gauge. So you do the same thing. You'd find that it's smaller than 2%. I think that is the best. Seems to me when we do the 10 gauge, you end up exceeding 2%. So if I select this, we'll find, and this just gives you the answers here. We take these numbers, 0.5, we're at, let's see, solving for A, 8.5 times 0.51 ohms times 0.2 gives us 0.867 volts. That's only going to be about 1% of 90 volts. B, it's going to be about 1.5% or so, 1.4%. And then if we solve for C, it ends up at 2.193, or basically, because it's a 90 volt system, more than 2%. So the answer is going to be B. Little bit complicated, but not terribly so. To power a 24 volt DC water pump with a 12 volt battery, you need to add, well, a better solution than this would just simply be to get 2 batteries and hook them up in series. You'd then have a 24 volt system, but that wasn't your option. So what you're going to need is a DC to DC voltage converter. to take your 24-volt pump, you can then convert your DC battery to a 24-volt system. And typically, of course, you would then have your amps double your voltage. For a system like that, it wouldn't make a lot of sense. You just get 2 batteries. But for, say, for instance, electric fence, if you're operating a DC system at, say, 3,000 volts or 4,000 volts, clearly you wouldn't hook up enough 12-volt batteries to get to 3,000 volts. So, so a DC voltage converter, just trying to make you aware that these things do exist. And then we get to the electric fence thing, and it says, okay, you want to do a solar powered electric fence, operate 24 hours a day. Well, that right there is a clue telling you there's going to be a battery involved because it's 24 hours a day. Panels at 12 volts, which would tell you your batteries have to be at 12 volts as well. You test the fence and find it's generating 2,000 volts. Well, we've got a 12-volt battery, 2,000 volts, so we need a DC to DC voltage converter. So you look through all of these things, and it turns out the last one, the PV panel, a DC disconnect, charge controller, 12-volt battery, and a voltage converter is going to be your right answer. Everything else here has like some AC stuff, like an inverter, AC disconnects. Well, there's no AC in this system. So this is a total DC system. So it's just kind of asking you to walk through, put a little logic into what it is. So if you go to Tractor Supply and you buy one of those DC voltage electric fence units, that's what you're going to be getting in your packet there. An array of 24 volts or 24 panels with an ISC of 8.5 amps has been configured into 4 strings, 6 panels each. The wires of these strings are combined in a combiner box. What's the minimum ampacity required for the wire in the AC disconnect or in the PV output circuit? So let me go in and just draw what we're talking about here. So what we're saying is we've got a solar array. All right. And we're coming in, and I'm not remembering exactly. Was it 4 circuits? I think that's what it was. And each one of them, each of these circuits had 8.5 amps. 4? Yeah. Okay. And so we're coming into a combiner box. So this is your combiner box. Each circuit is 8.5 amps. Well, what happens in the combiner box? Well, okay, I guess what we need to do first, just to make this a little bit easier, is we're saying that the output of the panel, the output of the strings is 8.5, but to size the wire, we need to take 8.5 amps times 1.25, which is the NEC safety margin. And then for solar, they require that you do another 1.25, which is the solar safety margin. And the reason why we're doing it twice is, you remember, these numbers are based on standard test conditions, and standard test conditions assume that you have a 1,000 watt per square meter. But if you remember, at the outside edge of the atmosphere, we can have as much as 1,300 watts. And on a very clear day, I've gotten measurements as high as 1,200 watts or 1,200 watts per square meter. So the amperage might actually be higher than standard test conditions. So if we take 8.5 times 1.25 times 1.25, and we're going to get, let me see, I'm showing 0.93, but that can't be right. 8.5 times 1.25 times 1.25. Yeah, 13.28. All right, so 13.28 amps. So our wire has to be sized to carry 13.25 amps even though we're expecting there's only going to be 8.5 amps coming out of the wire. And that amperage is going to be based on the ISC, not the IMP. So that's even going to be an escalated estimate. So we're going to oversize our wire by quite a lot. Now, what you're going to find is this portion of the circuit, the PV source circuit, is going to be the pigtails that are already wired from the panels. And they're usually 12 gauge in today's market. And if you look on the chart, if memory serves, that's going to be somewhere in the 20 to 25 amp range. I think it's around 20 amps if you read the first column. So that's more than enough for that. Okay, now if I needed to put a breaker, a circuit breaker in here to protect each of these strings, I would end up putting 4 single pole breakers in here. What size breaker would I put in? Well, typically they want you to round up to the next available size. So 15 amp breakers would be put in here. In theory, you could get away with 10 amp breakers because you're really only going to be throwing 8.5. But to meet what they're looking for, you want 15 amp breakers. Now, what the question was what would be the output amperage? Because this is the PV source circuit here. And we're looking for the PV output. And this is one reason why I wanted you to understand those terms, because oftentimes people will say, they're referencing these terms, PV output circuit, PV source. You need to know what they're talking about. So one of the purposes of a combiner box is to take multiple strings, combine them in parallel. Well, when you hook things up in parallel, the voltage remains the same, but the amps increase. Well, if we're coming in at 8.5, or now we've already done it times with the safety margins, 13.28, we're hooking up 4 of them. We just take that times 4, and we're going to end up at 53 amps. And so the wire has to be sized to carry 53 amps. I don't need to do my safety margins anymore because they were already built in up here. Or I could start out and I could say 8.5 times 4, and I would get, what's that, 34? And then I would do times 1.25 times 1.25. And I should get the same number, hopefully, if everything's right. So hopefully that makes sense to everybody. Oops. So I'm gonna take that off of there. Jump back in here. So we find 52.19, check, and that should be the correct answer. Boom. And it's telling us times that, 13.05, and then 13.05 times 4. Okay, if wire in a PV array is placed in conduit and exposed to sunlight, the ampacity rating for that wire must be adjusted by 1.25, increase, be adjusted by less than 4. For less than 4 conductors or not exceed 23 amps. Well, we don't have enough information here. We don't know where it is, if it's lying on the surface, if it's lying above the surface. So we're going to just say the heat from that is because of it's exposed to sunlight, the ampacity rating has to increase. It used to be that the NEC would tell us, they had a little table, and it would say if it was this many millimeters off the surface, you adjusted by this temperature, this many off the surface, it was that. They've made it a little bit less complicated recently. Now it's like if it's laying flush on the surface, you've got to increase. I guess they assume that if there's some air circulating around it, it's not going to increase the temperature within the array that much, or within the conduit that much. Yeah, John?
That was all faulty science when they did that ridiculous derating. They later on redid the testing and figured out, oh, wait a second, this is wrong. So that's where the new temperature rating came from. Faulty
Okay.
science for the first one. They had
Yeah.
the conduit capped off, and they did the temperature rating, but they were looking at solar ovens because
Yeah.
there's no circulation. That's what happened. So they redid it without capped off conduits and go, oh, wait a second. So that's what happened.
Yeah, I wondered about that because they made no differentiation between the
Well,
size
now
of the
you have
conduit.
the code mucked up. The code face planted. Oops, sorry, but they've done that more than once. But you know, it's all, you know, it's better to be too safe than not safe enough.
Right. Well,
But
they
there
do.
have been more than one embarrassment in the code.
Yep. Well, they do actually now sell often offset footers for your conduit. So if you have to run your conduit and expose it to sunlight, they have little pedestal footers to raise them up off the deck so that there is no requirement, no need to adjust for temperature. The code still says if you're laying it flat on the roof, you've still got to do a temperature adjustment. You know, if that
Yes, well,
conduit is lying on the roof.
but depending upon what the roof is, uh, you know, we just put cinder blocks up there instead of paying $12 on this fancy little thing. Just put a like $2 cinder block up. But you know, that's just whatever.
Yeah, that would
Same
work
deal.
that would work if you're working on a flat roof. But
Right.
if it's a shingled pitch roof or something, you know, then you gotta go with or the better solution is to run the wire
That's
underneath and penetrate under your array, and that way visually it just looks a lot better. Okay. You've installed an array of 24 panels, each with the IMP. This is kind of going back to the drawing I just did. This is a little bit of a red herring. It's saying you've installed the 24 panels with 8.35, 4 strings, 6 panels each. Assume that the source circuit has been placed in conduit that's exposed to sunlight. It's mounted directly on the deck of the roof. These conduits run to a combiner box that's mounted on the north wall of the home and is never exposed to sunlight. What is the minimum ampacity rating of the circuit breaker connected to each source circuit? Well, what I'm trying to get at here is basically to make you begin to understand that if you have to make an adjustment for temperature, what they're saying is that this is exposed to sunlight, and then this combiner box is not. One thing people get confused with is making the adjustment for temperature does not change the number of amps that are flowing through the wires. So once you're back into a situation where temperature is not being affected by sunlight, the same number of amps are coming through. So you would go with a 15 amp breaker. The temperature adjustment is dealing with the fact that the wires are not capable of carrying as many amps as they were rated for. So you need to put a bigger wire in, but you're not increasing the number of amps flowing through that wire. So that's the subtle distinction that you gotta sort of begin to understand. So when you're making temperature adjustments, you're simply adjusting for the ampacity characteristics of the wire, not the number of amps that are flowing through that wire. Hopefully that makes sense to everyone. An AC disconnect should comply with all the following except, all right, it needs to isolate the PV system from the grid for sure. Must be located at least 10 feet away from the point where the PV system connects to the grid. No, it needs to be located within 10 feet of the meter, which is basically the demarcation point. Externally operable, yeah. Must be clearly marked, yes. So we're saying it has to be located within 10 feet of the demarcation point, and typically in a residential situation, the meter is your demarcation point. That's demarcation point basically means where the utility's responsibility ends and your responsibility as a homeowner begins. With commercial systems, the demarc point could be somewhere different than that, than the meter itself, because it can be much more complicated. There can be multiple services coming in. A charge controller must be compatible with all the following, except, should it be compatible with the battery bank's nominal voltage? Yeah. The array's nominal voltage? Yes. The inverter's power rating? Well, let's look at that, and the array's output. So let me show you in the drawing here. We'll make this our last one, then we'll, what I'm getting at here is this is your array here. You go, typically you're going to come to a DC disconnect. Then you're going to go to a charge controller. Then you're going to go to your battery bank for a standalone system. Then you're going to go to your inverter. Then you're going to go typically to the load distribution center here. All right. So the purpose of a charge controller is to control the charging process from the array, which is the power source, to the battery bank. Well, if the battery bank is, let's say, 48 volts DC, the charge controller has to be compatible with that. It's got to be 48 volts DC to meet that. Now, if the array, in the old days, this would have had to be configured to 48 volts as well, because coming from the array to the charge controller to the battery bank, now the inverter would have to be 48 volts as well, input DC. Output, well, with a standalone, it could either be 120 volts AC or 240 volts AC, typically. There were very few three-phase systems, so these would be your only choices here in the US. So this is the way it was done for years and years and years. So your charge controller's got to be compatible with the output of the array, the input of the battery bank, but it never touches the inverter, so it really doesn't care what the inverter is doing. In fact, if it were an all DC system, there would be no inverter in the system. Now, one thing that you'll run across now, and very common, is an Mppt charge controller. And I don't like that term because they're basically saying it's a maximum power point tracking. Well, all systems have maximum power point tracking to keep your array and your system operating at its maximum power point, that to keep it at the sweet spot. But we would run into some serious voltage drop issues because doing a 48 volt array, this thing might be 200 feet away. And so you'd have to use some mega sized wire to get from the array to the charge controller. So what somebody came up with, and it really is a buck boost charge controller or a DC to DC voltage converter. So today's world, you can often get charge controllers where the input can be 600 volts input and then 48 volt output. So within the charge controller, you've got a DC to DC voltage conversion going on. So under that scenario, you can go as much as 600 volts DC on your array, and that will allow you to configure your system with longer strings, fewer strings, and smaller wire, because for the same amount of output, basically, you know, the same amount of power, you're going to be increasing your voltage dramatically, which means you decrease your amps, which means you put in smaller wire. And that can help your system be much, much more affordable. Okay, so let's go ahead and quit right there on Tuesday. We'll go ahead and finish up some of the discussion here, but I know we're going to get into some math questions. If you've got some sample problems that you want to work through, maybe a situation in your home where you want to install a system and you want to try and size it. If you get your electric meter or your electric bill, and let us know what the consumption is. We'll use those problems and work them out. So figure on Tuesday, we're going to walk through some of the math problems, the sizing problems, and same thing on Friday of next week. All right. So any questions before we call the end here? Okay, so I'll see you guys all on Tuesday. All right. Take care.